In this video, we're going to talk about exponential functions word problems involving logarithms. And this is the second video in a two-part series on exponential functions word problems. As we've seen in the first video, exponential function word problems are generally answered by using the formula a equals p times b to the n. A refers to the amount after all of the increasing or decreasing, p is the amount before, and b is the multiplier. Well, sometimes we know the values of a, p, and b, and we're trying to determine the value of n. When we're seeking the value of a variable found in an exponent, we use logarithms. So we're seeking the value of n, and it's in an exponent, so we're going to be using logarithms. And a lot of times, as we'll see, these questions are the types of questions that ask you, how long does something occur? It's asking you for a time, a length of time. Well, let's talk about logarithms first. A logarithmic equation is the inverse of an exponential equation. So for example, since 2 to the 3 equals 8, we can say that the log base 2 of 8 equals 3. And we'll discuss this a little bit more, but basically this is a mathematical thing where if 2 to the exponent 3 is 8, then the log, whatever the base of the exponent is, becomes the base of the log. So since the base of the exponent is 2, the base of the log will be 2, and we can say the log base 2 of 8 is equal to that exponent, which is 3. We use logarithms when we're trying to determine the value of a variable that is in an exponent. So for example, if 1.05 to the exponent n is equal to 1.885649, then n, the exponent, must be equal to log base 1.05, base of the exponent, of 1.885649. Using our calculators, we see that n is approximately equal to 13. Now, let's talk a little bit about log base 10, because not all calculators can handle logarithms in any base. We just did a question where we needed to know the log base 1.05 of a number because the base of the exponent we were dealing with was 1.05. But not every calculator can handle that. So many calculators only have a log button. If you see a log button with no base indicated, literally just the word log, the base is assumed to be 10. So for example, the log of 1,000 is the log base 10 of 1,000, which is 3. Now, why is the log base 10 of 1,000 equal to 3? Because trying to evaluate the log base 10 of 1,000 is like asking what exponent could go on a base of 10 to give an answer of 1,000. And since 10 to the exponent 3 is 1,000, therefore the log base 10 of 1,000 is 3. Now, before we get into the questions, a useful rule about logarithms. The log base a of b is equal to the log of b over the log of a. This rule is useful for people whose calculator cannot handle logarithms other than log base 10. Word of warning, if you have a calculator that can handle logarithms other than log base 10, it's still useful for you to know this because you won't always have that calculator at your disposal. And if you ever have a calculator that doesn't do that, you still want to be able to answer the questions you get. So getting back to this, using our previous example, suppose you're working on a word problem and you get 1.05 to the n equals 1.885649, but you only have a generic log button. Then you can say this, n is equal to the log of this number over the log of this number. The base of the, when doing this new method, this other method, the base of the exponent goes in the basement of the fraction. That's kind of a cheesy little way of remembering it. But the log of 1.885649 over the log of 1.05 will be the answer. And if you plug this into your calculator that only has the generic log button, you will be able to answer the question. So it's a good thing to know. So let's do some examples. Suppose a house appreciates at a rate of 5% per year. That means increases. If the house is worth $100,000 today, how long will it take for the house to be worth $188,565? Well, this question is asking us to answer in the form of a length of time. That tells me we probably are going to need to use our logarithm button, but let's set it up the way we normally do and see if that is correct. A is equal to 188,565 because that's the amount after all of the exponential growth. P is equal to 100,000. The base is 1.05 because we're increasing at 5% per year. 1 plus 5% is the same as 1 plus 0.05, which is 1.05. N is what we don't know. A equals P times B to the N means 188,565 equals 100,000 times 1.05 to the N. We want to isolate 1.05 to the N, so we divide both sides by 100,000. 188,565 over 100,000 equals 1.05 to the N. Method 1 is if you have a calculator that's pretty good. That means this statement means that N is log base 1.05 of this quantity. And if you have a really good calculator, that's 13 approximately. Method 2 is used if you don't have a calculator that can handle log base 1.05. In method 2, you say N would be the log of 188, right here it is. N would be the log of actually, I wrote this incorrectly. My apologies. N is approximately equal to the log of 188,565 over 100,000. So the log of this quantity divided by the log of this quantity. All right, a little typo on my part there. Sorry about that. Anyways, when you do that, when you plug that into your calculator, the log of this quantity divided by the log of this quantity, most calculators can handle that. Any scientific calculator can. The answer will be approximately 13. So N is approximately 13. Now going back up into the original question, we see it was asking us how long will it take, and it was 5% per year. So this 13 refers to the number of years, and we can say it will take approximately 13 years. Okay, in the next question, suppose a city's population decreases at a rate of 4.2% per year. Well, if the population of the city is 62,217 today, we want to know how long it'll take for the population to be 30,000. Well, this is a case of exponential decay. So the final amount is the smaller amount of 30,000. That's how much is after all the decay. The initial amount is 62,217. We know we're decreasing at a rate of 4.2%, so we know our B value will be 1 minus 4.2%. 4.2% expressed as a decimal would be 0.042. 1 minus 0.042 is equal to 0.958. So that's the base of our exponent. N is unknown. So A equals P times B to the N. We can say 30,000 is 62,217 times 0.958 to the exponent N. Dividing both sides by 62,217 tells us that 30,000 over 62,217 will equal 0.958 to the N. Now we do our method 1 and method 2. If you have a really good calculator, N is equal to the log base 0.958 of this quantity, which is approximately 17. If you don't have a really good calculator, you can say N is equal to the log of this quantity. So N will be the log of this divided by the log of this. The base of the exponent goes in the basement of the fraction when you're using this second method. So the base of the exponent is 0.958. So log of 0.958 goes in the denominator. Log of this goes in the numerator. Putting this into a calculator tells you it's approximately 17. So we know it's going to take approximately 17 years for that city's population to decrease to 30,000. Now, what if we have a half-life of a substance known to be 325 days? We want to know how long it'll take for 9,000 grams to reduce to 1,500 grams, and we want to round our answer to the nearest day. So we can say the final amount is equal to 1,500. The initial amount is equal to 9,000. So this is the amount before the decay. This is the amount after the decay. A half-life question has a base of 1/2, and N is unknown. A equals P times B to the n. So 1,500 equals 9,000 times 1/2 to the exponent n. We want to isolate 1/2 to the exponent n, so we divide both sides by 9,000. So 1,500 divided by 9,000 equals 1/2 to the exponent n. Using method 1, this is for people with really good calculators, we can say n will be log base 1/2 of this quantity. Log base 1/2 of this quantity. And that is equal to approximately 2.5850. Under method 2, this is what you would use if you didn't have a really great calculator. You would say n is the log of this over the log of the base of the exponent. And that is approximately 2.5850. Now remember, n is measured in half-lives. So that means it's going to take approximately 2.5850 half-lives. Well, the question asks us to round to the nearest day. So how long is a half-life? Thankfully, the question tells us it's 325 days. 2.5850 half-lives times 325 days per half-life means that the answer is approximately 840 days. So in the situation described here, it would take approximately 840 days for the substance to decay to 1,500 grams. And now let's get to our last question, and this is a bit of a toughie, so there's going to be a few steps here. Let's go for it. We know there are 300 grams of mathium today, but we know that there were 50,000 grams of mathium 80 days ago. So over 80 days, it's really decayed quite a lot. We want to know the half-life of mathium. If something decays, we know it's got a half-life. And this question asks us to round our answers to the nearest minute, but to express our answers in days, hours, and minutes. Okay? So let's start by saying our final amount is 300. Our initial amount is 50,000. The base is a half because it's a half-life question, and the exponent n is unknown. Well, the final amount equals the initial amount times 1/2 to the exponent n. Dividing both sides by 50,000 means 300 over 50,000 is 1/2 to the exponent n. That means n is equal to the log base 1/2 of this quantity. Now, if you have a really good calculator, the log base 1/2 of 300 over 50,000 is approximately 7.3808218. If you don't have a great calculator, then you can rearrange this a bit by saying that n will be the log of this quantity divided by the log of this quantity. So the base of the exponent, that 1/2, when you're using the second method, goes in the basement of the fraction, the denominator. So again, if you don't have a great calculator, n will be the log of 300 over 50,000 divided by the log of 1/2. And that is approximately 7.3808218. You might wonder why we're using so many decimals. It's because we're rounding to the nearest minute. So since the total number of days was 80 and the total number of half-lives was approximately 7.3808218, we can say that 80 days is approximately 7.3808218 half-lives, which means 80 days over 7.3808218 half-lives will give us the days per half-life. Days in the numerator, half-lives in the denominator, days per half-life. 80 over this is equal to 10.838901. So in other words, we know one half-life is approximately 10.838901 days. Well, that's like saying 10 days plus 0.838901 days. Well, let's figure out how many hours there are in 0.838901 days. 0.838901 days times 24 hours in a day. The days cancel out. We're only left with the units of hours, and 0.838901 times 24 is approximately 20.134. So we've got 10 days, and we've also got 20.134 hours approximately. Well, we know 20.134 hours is obviously 20 hours plus 0.134 hours. So we know we've got 10 days and 20 hours and some more time here. Well, let's convert that to minutes. 0.134 hours is equal to 0.134 hours times 60 minutes per hour. The hours cancel out, and we're just left with minutes. 0.134 times 60 is roughly 8. So we can say the half-life of Mathium is approximately 10 days, 20 hours, and 8 minutes.